Hello everyone, welcome to this next video on classical mechanics. In this video we shall see some generalized notations which are used in the derivation of equations of motion. These are displacement, velocity, acceleration, momentum, force and potential. Right. So let us first discuss what is generalized displacement. Usually we know displacement in general sense is this: we have this coordinate system, we have some particle over here. Now this particle, when applied some force, moves into this direction to this place. Now it again move to this place, right? And it then comes back to this place. So the overall displacement of this particle would be this distance, right? Sorry, it would be 0 because it comes back to its original position, right? So the distance between the original and the final position, that was known as displacement. Now we are talking of about displacement in terms of generalized coordinates, which we have discussed in the last video. So let us assume we have n particles in 3 dimensions. That means, according to previous video, we can define that n particles as one system in 3n coordinates whose position vector Ri is given by q1, q2 up to q3n. These are the 3n generalized coordinates, and t, where t is the time variable, right? So now let us assume in this case that time is fixed. So the displacement, virtual displacement denoted by delta Ri, this is calculated by differentiating this factor, right? So now this Ri, this is depending on q1, q2, q3 up to q3n and t. So these are the independent variables and Ri is depending on these. So if we are to differentiate this Ri, then we have to differentiate it with partially with respect to q1, and then then we have to take the derivative of q1. Plus we have to differentiate it with respect to q2, then we have to take the derivative of q2, and so on. So when you differentiate this factor, you will get delta Ri. This is equal to del Ri divided by del q1, then the derivative of q1 plus del Ri divided by del q2 into delta q, and so on, right? Del Ri divided by del q3n, then delta q3n, plus the last term would be del r divided by del t, then the derivative of this t. Now because we have assumed t to be fixed, therefore this del t is 0, therefore this last term won't come. So this term could be written as summation j varying from 1 to 3n delta Ri. This Ri is the position vector for the ith particle, right? Divided by del qj into delta qj. Now this delta qj, this is known as the generalized displacements, right? Whereas this delta Ri was our displacement in the usual sense. So now, do you know the difference between this dx and delta x? Dx refers to very small change, a change that is infinitely small when the limit goes to 0, and delta x is a change which is somewhat larger than this change, right? So after having understood what is generalized displacement, let us now understand what is generalized velocity. In usual sense, velocity is the rate of change of displacement. So here also the generalized coordinates are given by qj's, right? So when you differentiate this qj partially with respect to, not partially, completely with respect to time, then we just put a dot over here to represent that derivative. So by dot we mean we are differentiating the variable qj with respect to time. So now in here we have the position vector Ri as this, and we are assuming an unconstrained system. That means no constraint is working on our system as of now. So we can differentiate this Ri. So Ri dot with respect to this time variable t, so it would be Ri dot, this is equal to, again this Ri is a function of q1, q2 up to q3n and t. Therefore, we'll again apply the chain rule for and taking the partial derivative of this Ri with respect to q1, and then the derivative of q1 with respect to t, plus the derivative of Ri with respect to q2, then the derivative of q2 with respect to t, then the derivative of this Ri with respect to q3, and then the derivative of q3 with respect to t, and so on. And the last term would be the partial derivative of this Ri with respect to t, and then the derivative of t with respect to t, which is equal to 1. So this term is 1, right? So we can write it like this, and then we can club all these terms containing qj's into one summation. So this would be the factor when our system is unconstrained. So these qj's, qj dot, these are known as the generalized velocities. And if our system has k constraints imposed on it, the holonomic constraints for an n particle system, so the degrees of freedom, which earlier was 3n, now reduced to 3n minus k, let us call that by f. So our velocity Ri dot, this simply reduces to summation j varying from 1 to f now, right? And del Ri divided by del qj into del qj dot plus del Ri by del t. So the only difference is here we have j varying up to 3n, and here it varies up to f. So these qj dot, these are the generalized velocities corresponding to the generalized coordinates qj's, right? So now let us now move on to generalized acceleration. Generalized acceleration, as you might be guessing, we have differentiated this position vector Ri to obtain the velocities, generalized velocities. Now we'll differentiate it again to obtain the generalized accelerations, right? So we had this relation as we have just derived above. We can differentiate it again with respect to this coordinate t. So here what we do, we just differentiate this whole factor with respect to time. So in the first factor we have two terms. So we have to apply the product rule for differentiation, right? So we'll take the derivative of this first term first, keeping second as such, and then we'll differentiate the second term keeping the first term as such. So it would be ddt of del Ri divided by del qj into qj as such, and then the first term as such, the derivative of this with respect to time, it would be double dot over here, and then the derivative of this term, it would simply be this. Now here we have this term simply becomes Ri dot, right? And here also we have this term, so this also becomes Ri dot. So we can replace the values of Ri dot from here and here using this equation. So when you substitute this equation into this and simplify the things, our final equation becomes this. So now here you see the computation from the usual accelerations to the generalized accelerations, which would be qj double dot, qj dot, qk dot, qj dot. So these are not really so simple, and they are not linear functions of qj double dot as were the case with in the generalized velocity and generalized displacement. Here Ri dot was linearly dependent on qj dot, and similarly with displacements, right? So what we do, we have some other approach called the Lagrange approach, which simplify this calculation much more, so that equations of motion are obtained very easily, right? So next is the generalized momentum. In Cartesian coordinates, we have kinetic energy represented by this t as given by this expression half mv square. Now this v, that is the derivative of x with respect to t. The position vector, when it is differentiated with respect to t, we have v. And you can write this thing as x dot, the derivative of x with respect to t. So you can write it as x dot. So this v becomes x dot. So half mv square becomes half m x dot square, right? And momentum represented by p, this is given by mv. So now again you replace this v by x dot. So now you see we have this term as t. If you differentiate it with respect to x dot, remember we are differentiating with respect to x dot, so you'll obtain this half cancels with 2, this thing, you'll obtain this thing. So del t by del x dot is this, so half cancels with this. So and what is this? This is p. So we have this expression in the usual sense. But now we are talking about generalized coordinates. Therefore, the partial derivative of t with respect to the generalized coordinate. Earlier we were taking the Cartesian coordinate x. Now we will take the generalized coordinate. This is equal to momentum. So this momentum, when you differentiate the kinetic energy with that of the generalized coordinate, you will get the generalized canonical momentum. So this expression is important. Moreover, for any conservative system, the potential V, this does not depend upon Q dot. This thing is true. If it does not depend on Q dot, that means the derivative of V with respect to Q dot, it would be 0, right? So we can add it on either side. So we can write this as del t minus v divided by del q dot is equal to p plus del v by del q dot, right? Because this factor is 0, so it makes no sense, no harm writing this. And this quantity t minus v, this is L, and this is called Lagrange, whose details we shall be seeing in the next video. So in some instances, like in solving some questions, you can also use this expression del L by del Q dot is equal to P, provided your system is a conservative system. Moreover, one thing is important, that generalized momentum P, it may have dimensions other than that of linear momentum. The dimensions for linear momentum are m, L, t minus 1, mass into that of velocities, right? And suppose your generalized coordinate is angular coordinate. In that case, our momentum becomes ml square t minus 1 instead of mlt minus 1. And suppose we are in polar coordinates r and theta. In that case, linear momentum is given by taking the derivative of kinetic energy with respect to r dot. So it would be mr dot, and if you take its derivative with respect to theta variable, theta dot, it would be mr square theta dot. This is the angular momentum. But if you but you can notice here that the dimensions for P, the generalized momentum, and whatever the generalized coordinate you have taken for your system, the dimensions of this whole thing is equivalent to that of angular momentum always. No matter what coordinate system you are defining, when you differentiate, when you calculate P out of it, that means you are taking, you are calculating the partial derivative of T with respect to Q dot, and then you are multiplying it with Q. This thing is would always have dimensions of angular momentum. So on the similar line, we can discuss generalized force. Force usually is, work done is defined as force into displacement. There is no doubt with that. Therefore, the work done by some force, it is defined by summation Fi, because we have a large number of particles, n particles with us. So force corresponding to each particle is given by F1, F2 up to Fn. Therefore, we're taking the summation of these on the system of n particles. And we have small displacement, del Ri summation. Then the work done is defined as force into displacement for n particles. This one is for one particle, ith particle, then you can sum all those, so you'll get the change in the small work done, right? And we have just calculated the generalized, the value of this displacement vector, so we can use that values, right? These we already know, these are the generalized displacements, right? So we have utilized this expression over here. So we can shift this summation out, and we can call this term as Qj. So this work done becomes Qj into del Qj. So now you saw we started with this Fi, force into displacement. We end up at Qj into delta Qj. This is the generalized displacement. And this is known as the generalized force. Right? So this Qj defined by summation I varying from 1 to n Fi del Ri by del Qj. This is known as the generalized force. And moreover, similar to that of generalized momentum, the dimensions of Qj into Q, the generalized force, right, and the generalized displacement, when they are multiplied together, they always end up giving the dimensions of work. So similarly, this Qj may have any other dimension according to whatever coordinate system we have chosen. So that is it for this video. I hope these notations are clear to you. In the next video, we shall see what are the Lagrange equations and how can we obtain the equations of motion when we are talking about the notations in generalized form. Well, thank you for watching.